Design Prize. And that's for James Ogilvie and Michael Henning. Come up, come up. Sure.
Thank you. Ready? 1, 2. Thank you. Well done, guys. And thanks again to Kim and Orica.
No worries.
Now, you don't have to stay. You can just exit stage left if you choose. Yeah. Thanks, guys.
Bye.
And it's not just aspiration was that last 1 or 60 seconds. Thank you for your moment of glory. Now I'd like to welcome Dr. Peter McGowan, a recent...
No, I'm not the chief mechanical.
Oh, recently retired engineer. So I haven't got time to change it right now, Peter. Sorry. So, well, Peter will update you on his current status. And while Peter comes to the stage, I will put his PowerPoint presentation up. So just any button will do.
Thank you very
Over to
much.
you, Peter.
Thank you very much. Good morning, ladies and gentlemen. Yes, I'm certainly no longer the chief engineer. I'm now officially a has-been. So I'm officially over the hill and all of those things, which means I've been able to sail off into the sunset and have fun, which is what I'm now doing. But Colin's asked me to give you some experiences of my 40-year career while I was still earning a living. I want to talk today about the laws of design, which are much the same as the laws of project management. Here's my first law. For every $1 a project is underestimated, it will be overspent by $3. Further, except in very unusual circumstances, a project is never overspent. What this means is you can construct a cost estimation curve like this. Now on the vertical we have the actual cost divided by the real cost. The real cost would be the best cost if everything went right. On the horizontal axis we've got the estimated cost divided by the real cost. So these two axes have been normalized against the optimized cost. And you'll notice that these consist of two simple straight lines. This section here is the underestimate, and that section there is the overspend, which means that if you want to get a minimum cost project, then the best way to get a minimum cost project is to actually get the cost estimate right. Let me give you an example of this. We had a project a few years ago. It was estimated at $32 million. That was about right in my judgment. It was regarded as too much. It was cut back to 20 million, and they stopped spending at 50 million. It was also a year late. The problem here is that when you underestimate a project, you know where you want to end up, and to underestimate a project, you invariably have to cut things out that are actually needed. And when you cut things out that are actually needed, to make the job work, you've actually got to put them in late, which means that you end up buying them in a hurry, they're badly planned, and you pay too much for them. And the upshot of all of those effects is that you end up running the project late, and secondly, you end up overspending dramatically. So you can't change the cost of a project by changing the cost of of the estimate. The cost is the cost. But some managers like to pretend that you can change anything by changing the estimate. So you'll end up with a job where you come in and they say, this is going to cost us this much. Oh, that's far too much. I'll allow this much. And you get halfway through the job and you realise you're not going to make it. And so you furiously have to start adding things back in, and it costs an absolute fortune. And because it was a year late, it also cost us about $1 million, $50 million of lost production, which means that an underestimate of 12 million ended up costing $30 million overspend and $50 million of lost production. A huge cost. But you'll notice there's another part of the curve there as well. If you overestimate a job, it will always be overspent. Because projects, except in very unusual circumstances, are almost never underspent. If there's money there to be spent, the project managers will find something to spend it on. Always. So the minimum cost always occurs when the estimate is most accurate and realistic. And that is an art, recognised for a long time by many companies. As a consequence, they have highly trained specialists to get the estimates right. Now, to get the estimate right, you've got to get the scope right. And I'll come to that a bit later on. Law number 2. The difference between a good and a bad designer or manager is the ability to make decisions early with scant information. Bad designers or managers will only make decisions when they have no choice, that is, when circumstances dictate decisions. The upshot of that is that bad managers do not manage. Now, you'll find this is absolutely a plague in the industry when you get out. There are a lot of managers who are nothing short of paranoid, who won't make any decision till they've got all the information. Now, the only time you can get all the information is at the end of the job. You never have all of the information. This is the real world. We cannot switch to another channel. And you have to make a number of decisions based on incomplete, conflicting, and sometimes difficult information. But that's what distinguishes a good manager from a bad manager. A good manager manages. A bad manager will wait until he hasn't got any choice, which means he's not managing. I'm sure the academic world is no different. Let me give you an example of the PVC plant that I was involved in designing many years ago. We had to minimise the number of plant items, minimise the height and scope of structures, and minimise field labour, and minimise space occupied. All these are designed to minimise cost. And they're good rules to minimise cost.
Excuse me,
Go ahead.
Just expanding on field labour, just so everyone's on the same page.
Ah, okay, sorry. In a big project, there are two types of labour. There's what's called shop labour and field labour. Shop labour is what's done in an engineering shop, somewhere, wherever it is. Field labour is what's actually done on site. Field labour is always, in round numbers, twice the cost, sometimes 3 times the cost, depending on where it is, of shop labour. And furthermore, field labour is never as good, because you're dealing with hand tools rather than, in the field, you don't have a beautiful big milling machine and a nice lathe. You always have portable welders, portable grinders, portable everything else. So what you always try and do is maximise the amount of work you do in the shop and minimise the amount of work you do on site. So ideally what you'd like to do, which you can't, is build the whole plant in a shop and just lift it up and drop it into the site. You can't do that. You've got to break it down into small enough pieces, whatever that means. And those pieces are actually getting bigger and bigger as time goes on. But what you do is you break it down into small enough pieces that you can then lift up and drop into site and simply bolt together in some way. So you minimise the amount of time you spend on site. Sorry, Kim?
I said also safer.
And you're absolutely right, Kim. If you have another brilliant comment like that, please don't be quiet. All right, this was the previous structure. This was going to be a doubling of the capacity of this particular plant. I was involved in the design of these 4 large PVC reactors, which went into a large, complex, and quite expensive building. You can see a close-up of one, and in round numbers, and you should start collecting these rules of thumb, a common industrial building will usually have between 5 and 10 kilograms of steel per cubic metre. This particular one had 16 kilograms of steel per cubic metre. That's a very heavy, expensive building. And the reason for that was because these large reactors, 40 cubic metres reactors, have big swirling masses, and you have to stop them swaying and rocking and things like that. So we had to put a lot of steel in it, which meant there's a lot of concrete as well to make them fireproof, and on and on. So the building was very expensive, and we said, is there a way of getting around this expensive building? This is what we designed. Because these reactors are very large and bulky, we said, why don't we use the reactor as the building and just put legs on them and then put a platform up the top, which is where we need access, and that will be the building. Saved an absolute fortune at the time. This is some time ago. People still do the same thing now, right? This is nothing strange. This was the benefit at the time. These were just in these reactors. This is not for the whole plant. It was a lower capital cost of nearly $1 million. Earlier operation, about another $1 million. There's also a bunch of other significant benefits out of a project cost of about $40 million. And had we built it the old way, that would have been about $50 million, all other things considered. So it was a very significant saving. Here's law number 3. And this is the one I want you to pay most attention to today. Sir? No, that's fine. There's no problem.
The first issue you mentioned about management. How hard was it for you to convince management of the merit of your idea for the PVC vessel you just talked about?
That's how I convinced them. Management only know one language, and that's dollars. If you can convince management by saying it will be cheaper and faster to do it this way, and there's a whole range of things that bear on that, and that is the actual cost of the equipment, the field effort in doing it, but nowadays people are now paranoid about another quantity called project risk. And what you do, managers don't understand risk, so what you've got to do is put that in money terms again, and say, well, the risk involved in this, if it goes wrong, is this much, or if it does this, it does this much, and you have to evaluate those risks in adding things up. And what managers don't like is when you come up with something that nobody's ever done anywhere in the world before, and it's so new that everybody says, oh, that's brilliant, but will it work? Has anybody ever done it? We don't know. Then the management risk is significant, and then they say, I don't know about that. Because most managers, in addition to being miserly, are also supreme control freaks. And most of them would actually prefer to spend a bit more than to lose control. But that's how you win every argument. There's only one language they talk, and that's money. And so you have to turn time into money, you have to turn risk into money, you have to turn everything into money terms and then add it up, and this is the total risk. And there are all sorts of rules about how you do that, but everybody understands those. Keep interrupting as much as you wish. People that work with equipment, this is law number 3, people that work with equipment know more about it than the designer. Now, remember that when you get out, you're going to have these shiny new degrees where you're going to be, in some quarters, a big shot. Don't let it go to your head. Make sure that the first thing you do is go and have a cup of tea or a biscuit or whatever with the people that operate the equipment. Make that your first priority and make sure that you learn as much from them, because I guarantee that by doing that you'll learn more from them in a month than you've learned in 4 years here. Now that's not to say you shouldn't have gone here, don't misunderstand me. But you need to go and talk to the people that operate equipment, because they do know a lot of things about it. Make sure that you stay good friends with them, very good friends. Let me give you an example. Some years ago, I was asked to go down to the Victorian Railways. In fact, I got a phone call. At the time, my office was only a block away from the engineering headquarters of the Victorian Railways in Collins Street. And I was rung up and I said, we want you to come down here immediately. I was working for Orica then, or ICI as it was at the time. And my boss said, they want you to go down. That's fine. You go down and do whatever you need to do with them. So I was ushered into their office in Collins Street. And when I was brought in, suddenly the office went quiet. We were ushered upstairs and into a large drawing office, which is always full of chatter. And it immediately went quiet. And I was ushered to a drawing board where there was a set of drawings showing this wheel set, railway wheel set, and beside it was another set of drawings showing a large hydraulic press. And I was shown these two items, and they said, what do you think? I said, that's a wheel and that's a press. And these people were almost bowing and scraping. I said, what is going on here, you know? So they said, we'd now like to take you down to the railway yards in Newport to have a look at these rail wheel sets, and then we'd also like to show you this hydraulic press. I said, okay. So we go down to the railway, Newport, big workshops down there. I'm not sure if they're even still there now. I think they might be apartments on them or something now, but anyway. I went down there and there was this huge 10-hectare lot. And it was gargantuan. And as far as you could see, there were these wheel sets sitting on the ground, all queued up. Thousands and thousands and thousands of them. And we were brought in and we were shown a true hydraulic press. That is one actually operated by water. Remember, hydraulic comes from the Greek word hydro, meaning water. And it was a press actually with a ram that actually operated by water. I said, this is the old press that we used to use. It's a 300-ton press. I said, well, what was wrong with it? Oh, it didn't have enough capacity. So what we did was, it would only get about 3/4 of these wheels off. Because what happens with these wheels, as trains run around the Victorian railway system, the brakes clamp on the outside of the wheel, on the circumference of the wheel. And as the train is braking, these wheels, because of the non-scleronomic action of the brakes involved, actually end up, instead of remaining round, believe it or not, they end up becoming polygonal, you know, the 10 or 12 sides. And after a while, as you're riding along these trains, the train goes clunk, 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 clunk. So they have to be brought in from time to time. They brought in over a big machine that they had down at Newport, where the train actually comes in, and a big machine comes in, it lifts the train up, spins the wheel, and a pair of calipers come in and actually machine the wheels round again, drops it back on the rail, moves along, and you actually can move through a train in half or between half and 1 hour, remachine the wheels on this train. Of course, you can only do that 3 or 4 times, and there's not enough material left on the wheel to do it again. So you've got to push the wheels off and then shrink fit a new set of wheels on the axle. So what they do is when the wheels get small enough, they have a detector say, oh, these are now too small, drop those off, put a new one on, and away we go again. And so the old wheels then they get melted down and they get turned into brake pads, which then get scattered. Apparently in Victoria, they scatter about 20 tonnes of iron around the tracks of Victoria every year in brake pads. Okay. So what they have to do is push these wheels off, the axles. So this was the So somebody said this old 300-ton press wasn't good enough because only 3/4 of the wheels it could push off. So they said, let's get a 600-ton press. In other words, if it's not working, get a bigger hammer. So they designed this press, and it was actually about a year late, and people were getting pretty frustrated and testy about this. They put the first wheel in, and the first thing that happened was that this collet, you see the collet there opposite the ram, that vertical section there. We haven't got a pointer here, have we?
Mouse.
Oh yes, see this one? Let's have a look. So, see this collet here? That collet there was originally 30 millimetres thick. And of course, as soon as the ram came against it, it just went... So somebody said, I got pretty grumpy about this. They said, well, order a new collet. If 30 millimetres is not thick enough, we'll order a heavier one, and this time we'll make it 80 millimetres thick. So then, with great fanfare, they finally start... Meanwhile, while all this is going on, the guys that are trying to be operating this press are sitting around playing cards, waiting for these idiot engineers to try and get their press ready so they can press this huge yard full of wheels off their axles. Meanwhile, they continue to accumulate. There's thousands of them out there. And these guys are sitting around playing cards while these engineers are mucking around with the press. So they put these, finally, they get this thing up, and they've got a decent-sized collet on it this time to try and press the wheels off. They put it on, and they get up to 280 tons or whatever it was, and the collet just goes again. Whereupon the chief engineer apparently lost his temper, and he was apparently heard to scream amongst the gurglings, get McGowan, which was 5 minutes later. I got this phone call to come down and have a look at this problem. And of course, I had no idea what was going on. I've never seen one of these presses. I've never used one. I've never tried to push things off. I had no idea what was going on. And they came into me, and all these guys are bowing and scraping like I'm the Hail Mary man or something, I don't know. And I only knew that I was totally ignorant. I knew less about this problem than they did. So I had a look at this, and I thought, I've got no idea how to fix this. Not the foggiest idea. So this is what they did. The collet sits on the back of the wheel, the hydraulic ram comes, presses on the end of the shaft, and hopefully the two-part company. And then you just press another one on, and away you go again. So I didn't know what the trouble was. So I said to them, gentlemen, let me think about this for a few minutes. I was standing around in this whole workshop, sitting around, just completely idle, waiting for, the words from God or something to come down to... And I said, by the way, who are the guys that are supposed to be operating this machine? I said, those guys over there, they've been sitting around playing cards like that for 2 years, waiting for this thing to get up and running. I said, do you mind if I speak to you? You may do absolutely anything you like. So I went over in the absence of these guys, and I said to these characters, you guys supposed to be operating this machine? Yeah. What do you think of it? Bunch of... I won't repeat exactly what they said. I said, why? What do you think's the trouble? He said, the old water-driven press was perfectly good. I said, but didn't it not get a quarter of the wheels off? Only gets 3/4 of the wheels off, and the last quarter went, and they needed a bigger one. He said, oh yeah, but he said, if it's not going to come off by 250 tons, it'll never come off because the shaft swells when you press it up to that amount. Now, these guys are tradesmen. They'd done it for years. They knew exactly what it was, and they had observed this. Suddenly, the penny dropped. I said, I know exactly what the trouble is. You see, as soon as you press that, a combination of the Poisson effect and yield actually swells the shaft, and if it doesn't come off before that effect occurs, it'll never come off. So I said, well, thank you very much. And I said to the characters, gentlemen, I've got to go back to my office now. I'd like to do a few calculations, and then I'll send you a recommendation. Remember, this has been going on for 2 years. I went back to the office, did the most simple calculation, force divided by area, and found that when I did that calculation, it produced a result bigger than the yield strength of the steel. Bingo. So that means that as soon as you get to that point, this thing's never, ever coming off, no matter how hard you press. Because the harder you press, the more friction you get between the two. So the solution was actually quite easy. You actually drill a little hole down through the thing for those that won't come off. You pump oil in there, and you can push it off with your finger. Didn't need the big hydraulic press. So I wrote a little report. It was a one-page report outlining all this information and sent it off the same afternoon to the chief engineer. And he immediately rang me up, and he was furious. He said, we've been battling this for 2 years, and you solve it in about 2 hours. And I solved it only because I talked to the guys that operate the machine who knew how it worked. The other thing that he said was that he was very angry precisely because this is what is done on ships' propellers to get them on and off, because you can't have presses big enough to do that. And it makes the job very easy. Because when you pump oil in here, the two surfaces get pressed apart, and you can press them off very easily. Law number 4. Sir. Yes, certainly.
Why? I get the idea that they want to separate the wheels from the shafts. Are the shafts so valuable that when they had that quarter that wouldn't come off, they just didn't melt the whole lot down?
I don't know the answer to that question. All that I can say is that was their practice at the time. I think that it might have changed now, but if you make, the alternative to that would have been to actually make them all in one piece, forge them in a single piece and machine them out of a solid. I believe they're starting to do that more now. But at the time, forgings of that size were rather tricky. Having said that, the materials in this actually vary quite a lot. The shaft itself is a mild steel. The wheel is a slightly better steel, and it's actually case hard. What I haven't shown here is that there's a case hardening, and in order to case harden it, you actually have to have the right material. So there's actually a tyre on the wheel that is a chrome moly type material. I didn't get involved in that detail, but that's no problem. Law number 4, the total cost of a commodity is equal to the unit rate multiplied by the amount. Now, I hope that I'm not embarrassing or insulting the intelligence of people here by enunciating such an obvious thing, but it still escapes many managers. Let me give you a perfect example. This is a large salt hopper that used to feed the chlorine plant at Botany. All chlorine in Australia now comes from a single company, and it all starts life as salt, and it goes into a series of electrolyzers which separate the sodium from the chlorine. Sodium comes out as sodium hydroxide. The chlorine comes out as gas. And the chlorine is sold mostly to purify water. If the production of chlorine stopped tomorrow, there'd be a massive outbreak of typhoid and cholera and numerous other things. That's what gives us our clean water supplies in Australia. Anyway, it all starts with this hopper, where salt is loaded into this hopper, and it's fed out of the bottom of the hopper into a series of conveyors which ultimately feed it to the electrolyzers. It was a large, very large hopper in carbon steel, but lined with ultra-high molecular weight polyethylene. The problem with dealing with salt, granulated salt, is that it's slightly deliquescent, which means that it absorbs water and tends to clump and agglomerate, which means that when you put it in an open storage like this, if you don't get it right, you end up with this gigantic salt lump, and nothing moves. if you get it half right, you get these lumps coming down, you get arching and bridging and all sorts of things happening. It's a very difficult material to convey. Well, the trouble is they designed this hopper and installed it actually standing on 4 legs. The 4 legs actually connect up to this joint. Legs are attached to this joint up here. Oops. And so the thing was actually running quite well until soon after it was installed, somebody noticed that it was a set of offices only 5 metres away from this on the ground. By the way, you can see this sits up about a total of about 10 metres into the air. 10 or actually the bottom of that's about 5 metres in the air, so it's about 15 metres in the air. It's quite high up. But it's nearly 8 metres diameter, as you can see. Anyway, there's some offices only about 5 metres away from its base. And people noticed that on a regular basis, books would go and fall off the desk. There's these mini earthquakes occurring. And they tracked it. They plotted this, and they found the centre of this was this hopper. And they found, furthermore, that when you looked up at it, sometimes in the north-south direction, it was a metre narrower than in the east-west direction, and at other times it was a metre narrower in the east-west direction compared to the north-south direction. In other words, the diameter was doing this. And somebody thought, if this thing falls over, it could do some real damage, because it held 400 tonnes of salt. Not that salt is toxic, obviously, but if it fell over, it would be embarrassing. Really ruin somebody's day in the office downstairs, although they would give up smoking forever, presumably. So they decided that they really needed to fix this to stop it behaving this way. And they noticed that, this is just some more dimensions. There's an outlet on the bottom of the thing. It's about 1 metre diameter, and there's a diverter valve at the bottom. And, or there was, but they then decided that they wanted to update this and change this to try and eliminate these mini earthquakes, as they called them, plus the changing diameters at the top. I knew this was going on, so I actually called them and I said, look, I think I know what the trouble is. Do you want me to come and fix it? And the site manager there said, what's your rate? My internal charge-out rate he was referring to. I think at the time it was about $80 an hour. And he said, oh, that's outrageous. He said, I've got another contract engineer I can employ for $40 an hour. I said, are you sure he knows what he's doing? And he said, oh, well, he's $40 an hour. He's got to be better. I said, up to you. All right. So he did all this. He produced a huge set of reports, these beautiful, pretty pictures full of finite element calculations. He did finite element calculations. I've never seen so many finite element calculations. And this was his first modification. He changed the bottom section a bit because that was where they were having to fix up lumps. And after that was done, nothing changed. It was still exactly the same. So I rang them up again. I said, look, do you want me to fix this? I think I know what the trouble is. And I said, what's your rate? I said, it's now $85 an hour. Oh, that's far too much. He said, I'm still going to hire this other guy for $40 an hour. Okay. So then he made another modification. This time he actually put a pneumatically driven ram inside the thing to help keep the thing moving, plus an extra annulus. It made no difference. So I rang them up again. I said, how much? He said, how much is your rate now? I said, it's now $100 an hour. He said, oh, it's outrageous. This other guy's still only $40 an hour. I said, it's up to you. So then he produced a third modification where he made even further changes to this outlet section of the hopper. He put in an extra standpipe and a 19-degree cone and a range of other things. It made no difference whatsoever. And by this time, the bottom of the cone is severely cracking. There's big cracks starting to appear. So they're going to have to weld this up, which is tricky because you've got high molecular weight polyethylene inside. So you can't just put a welding torch to it because you'll destroy the lining. So after the third modification had no effect whatsoever, I rang them up. I said, you sure you don't want me to fix this? Because I know what's wrong with it. And he said, what's your rate now? I said, it's now $126 an hour because there'd been some very serious rate rises. He said, that is absolutely outrageous. He said, can we do something about the rate? I said, no. He said, well, all he could talk about was the rate. So eventually, I think his boss eventually told him, let McGowan fix it. So I fixed it. And all it actually meant is the guy that was doing the job was actually concentrating on the symptoms rather than the cause. And he kept looking at this outlet down the bottom. What it really needed was a ring beam at the transition from the cone to the cylinder. And once that was fixed, all the problems went away. I knew that. It was very easy. And these were the final costs. The original hopper cost $300,000. It cost $200 of installation. The cheap analysis ended up costing $40,000. And the first set of repairs was $500,000. The subsequent sets of repairs were similar prices. My expensive analysis cost $700, and the final set of repairs that fixed it was $80,000. So you can see why the rate is irrelevant. What he should have asked is, how many hours are you going to charge me? Now, that's a real example, and I've had that happen numerous times. Here's another example. I had to build some sparge vessels not all that long ago, actually. And people said, why can't we get them made in Indonesia? Because their hourly rates are $5 an hour, and in Australia they're $50 an hour for a shop tradesman. Have a look at these costs. The ones made in Australia, the steel costs $7,500. The labour costs $50 an hour. Takes 900 hours to build one. Total labour cost is $45,000. Total cost of the vessel, $52,500. In Indonesia, steel cost is the same. Steel cost the same everywhere, by the way. Labour cost is only $5 an hour, 10 times less. It takes 8,000 hours to build one of these in Indonesia. Labour cost is $40,000. Transport is $5,000. Total cost, $52,500. Note that. The labour cost actually gives you an indication of the productivity. If labour costs were the determining factor for economic prosperity, Australia and America and Germany would have been broke years ago. The reason that China still cannot compete with Australia, despite having labour costs that are between 5 and 10 times less, is that their unit productivity costs are so much lower. That's what people keep forgetting. Consequently, China is good at making widgets, that is, millions of the same thing over and over and over again, but they're hopeless, frankly, at making high-quality one-off equipment. They just can't do it. Law number 5. Sir.
Given you have experience with that, I just hope you don't mind.
No, it's fine.
I often say to different ones, students and others, people learn, people will do better. You just mentioned China can't do the one-offs. Have you been to China? Have you got experience with
Yes.
that? They're getting better at it?
Not yet.
Okay.
Not yet. In fact, one of the last jobs I had before I retired was actually producing chlorine drums over there. If we produced the chlorine drums here, we wanted nearly 1,000 chlorine drums. We've produced them here. They would have cost us $9 million for these drums. Over there, they cost us $4 million. But so they actually were same company, by the way, plants, workshops in both places. Steel costs are the same. Labour rates totally different. The labour rates were about 10 times less there than here, but the total cost is only about half. So that indicates immediately what the part of the trouble. It took them an enormous amount of time to get the sausage machine up that they built to work, and even then, each of these Chinese people, which were highly trained local labourers and tradespeople, welders and fitters and all that took to make these things, there's about 1,000 operations that go into making a drum. Quite a number. If they were programmed to do this job, they would just keep doing it and keep doing it and keep doing it. And their mentality there and their culture is, I've been programmed to do this. Whereas the guy in Australia say, they told me to do this, but the guy's obviously an idiot. What he really means is this, and I'll do it this, and I'll do a better job. They don't do that in China. They just can't. In fact, it showed up because we actually paid a Lloyd's inspector to live in that plant full time. And I said, nobody will so much as fart or scratch their bum without this guy's signature. And he signed off everything and caught numerous problems along the way. People, not that they were being malicious or anything else, they just were doing what they had been programmed to do, and because the guy used slightly the wrong phrase or whatever, he was doing slightly the wrong thing, which had consequences, and it was traced back, and we had to adjust that or put in an extra jig to... Now, that just doesn't happen here. Now, that's not to belittle them for a moment. It's just that there's a difference in culture. They're very good at sausage machines. Very good, much better than we are. Consequently, repetitive manufacture is going to China. One-off manufacture is staying in places like Australia because you get a vastly better job. More quickly. Law number 5, commodity engineering is neither. That is, one can buy commodity analysis and commodity paper shuffling, but ingenuity is invested in creative individuals. Every innovation was created by an individual, then checked and implemented by a trusting team. Think about it, without exception. There have been almost nothing that has been innovated by large teams. Let me give you an example. I had to get a quote for some analysis not all that long ago. Company A was asked to quote for a pipe flexibility analysis. $76,000. Company B, which has just half a dozen individuals, Company A is a very large company. Company B is a very tiny company, just a few individuals. $13,500. They made a profit out of it at $13,500, which say, why is the large company doing $76,000 and struggled to make a profit? In fact, in the end, if they'd done it, it probably would have cost over $100,000 because they had all these people who just did these little bits and just shuffled paper. Not really engineering. I could quote many examples like this. On another occasion, the two quotes came out at $125,000 and $15,000 from the same two crowds for a similar type analysis. The small company still made a profit and did a better job than the $15,000 one for that sort of thing. Gilbert Chesterton said the whole difference between construction and creation is exactly this, that a thing constructed can only be loved after it is constructed, but a thing created is loved before it exists. That's the difference between commodity engineering, so-called, and design. Let me give you this final advice. Learn to do good engineering despite management fads and programs. For 40 years I was irritated by numerous fads that came along. I just kept doing my job. You just go along with them and smile and keep working. Practice the three prerequisites of successful projects. Tattoo these 3 laws on your brain. 1, get the scope right. 2, get the scope right. 3, get the scope right. Collect rules of thumb, such as this. Instrument engineers need twice as many IOs as they ask for. Software engineers will need 3 times as long as they request, always, without exception. I've never seen, and I've done a lot with them. Contractors' estimates are overmanned and underscoped. Vessel construction costs about $15 a kilogram plus $10,000 in carbon steel, and in stainless steel it's about an extra $5 a kilogram. These are rough rules of thumb that you need to collect so that you can do your job rapidly and keep your head above your colleagues. Be practical. Take every opportunity to get your hands dirty. Get a shed. Do not confuse activity for progress. That's a really common management mistake. Steel and concrete are cheap. Use them liberally. Don't skimp on cheap things. Thank you very much.
Thank you, Peter. Keep standing if you don't mind. We've got a few minutes left, everyone. Has Peter prompted a question from anyone other than me?
Or are they too much like zombies? Haven't had enough caffeine this morning.
I didn't quite understand why the wheels of the trains became polygons.
Look, I could provide a series of lectures on the fascinating physics involved in that, but suffice to say that braking is not a uniform, clean process. Especially when you're using cast iron brakes. In your car, there's an enormous amount of technology gone into making them smooth brakes so they don't squeak and scream. And that's one of the reasons why modern cars have a preference for disc brakes as distinct from drum brakes. Because drum brakes always judder. They go which is why they tend to wear that way. But ordinary car and truck brakes now are actually not made of cast iron. They're made of some quite complex materials to make the braking smooth. On trains, the brakes are just cast iron. In other words, they ram cast iron against hardened steel, and it's not a smooth process, and it actually judders. Very interesting piece of physics. I won't take the time to explain it further. Sir.
So this was prompted by the Australia-China manufacturing thing, but I'm just wondering if you have any concept on where Australia's manufacturing is going in the future?
Exactly where I hinted at. Australian manufacturing struggles with repetitive stuff because of the mentality and the culture in Australia is such that if you just ask an Australian to do the same thing all day, every day, they really struggle. Whereas the Chinese don't for some reason. Consequently, you can get things done repeatedly in China so long as they're properly supervised. You've got to supervise them within an inch of their life. You've got to have much higher rates of supervision in China than you do in Australia, but then you can get things done repetitively and in a quality fashion, providing you don't... one of the difficulties with China is the endemic corruption. There's much higher corruption there than here, much higher. And that's why part of the reason why you need much better supervision. But for one-off stuff, Australia will always be extremely good at few-off type things, making vessels and a range of other things. And that's why there's still quite a lot of manufacturing here. It's getting a smaller proportion of our economy, there's no question about it. But you notice all the things like footwear manufacturing's gone, textile manufacturing's gone, car manufacturing's gone, because that's repetitive. But the one-off stuff, I mean, there's a new Thornton Engineering just down halfway between here and Geelong. Enormous great shed that they've spent $600 million building in Australia because it's economic to do that here, for building large pressure vessels and piping systems, because they're all one-off. Sir?
Why do you think the submarines were manufactured to a different country then?
Well, they're not. They're actually contracted to a number of countries, and parts of them, we've actually had to buy the technology for those submarines from different places. Things like the profile of the screws, the profile of the hulls, very, very complex piece of fluid dynamics involved in those, because the whole art of a submarine is to stay quiet. And that's why they're always driven with electric motors rather than diesel motors. You only turn the diesels on anyway when you get to the surface because they have to breathe. But underwater, they're all driven by electric motors. So there are a number of parts that were bought in from other places, but a large chunk of them will still be done in Australia. The actual final manufacturing and assembly will be done here. It's not quite as simple as the media likes to portray. The media, in order to sell a news story, you have to create conflict. And therefore, conflict is always reduced as something to rather simplistic terms. And life is actually more complex than the media would often like to portray for the sake of a simple story.
I'll ask a question, Peter, just to finish off with. The class has just finished a little mini-series of lectures on systematic material selection, and an assignment was handed in last night. And we've talked about this in private, but just if you could just give everyone just an outline of the range of materials that you worked with or you selected in your career at Orica.
Oh, dear idea. Well, certainly I've played with a lot of...
I'll preempt you. Just so you see that going into all sorts of exotics often is a waste of time. Steel.
Well, you've got to use the most appropriate material. There's no question about it. There is a time and place for exotic materials, such as Hastelloys and fancy stainless steels. But you know, you've got to understand what is best for the right things. There's a right space for grey cast iron. There's a good space for ductile cast iron and spheroidal graphite cast iron and hardened stainless steel and softened stainless steel. And make sure that when you get out, you know more than just mechanical engineering. You do know a bit about materials. It'll be very handy for you.
That's a good answer. Thank you for that. So thanks everyone for coming. I really appreciate it, given that probably a lot of people are up till getting on to midnight finishing off your assignment. So thanks again. Just thank our guests again. I'll see you tomorrow. Well done. Thank you. Have you got time for a coffee?
Great.
Because of the irregular nature of salt,